Theory time is over. For the next 3 episodes, we build. We're going to take everything from this series and compose it into complete, real systems. And we start with the one you'll be asked to design most often, an order processing pipeline. The domain here is e-commerce, but the exact same shape applies to bookings, provisioning, insurance claims, anything that's a multi-step transactional workflow. Let's design it end to end. Let me walk the whole flow first, then we'll zoom in on the tricky parts. A request hits the API. The API assigns an idempotency key to this request. Then it writes 2 things in a single database transaction, the order row and an outbox row. A change data capture relay, Debezium, tails the database log and publishes that outbox event to an order events topic, partitioned by order ID. From there, several consumers react. An inventory service reserves stock. A payment service charges the card. And an analytics service reads the high-volume stream. A saga coordinates those steps. Finally, a fulfillment executor, a single consumer group processing each order in order, calls the shipping provider idempotently. And the result flows out to an order status topic that notifications, the search index, and reporting all consume. That's the map. Now the 4 parts that actually make it correct. Part 1. Idempotency, the double submit problem. A customer double-clicks. A mobile client retries a request that actually succeeded. Without protection, you create 2 orders and charge twice. So the API uses an idempotency key that's stable across retries, generated by the client or the gateway. Before creating an order, it checks. Have I seen this key before? If yes, return the original result. Don't create a second order. If no, create it and store it against the key. And that key flows through every downstream hop, so each stage can dedupe too. Part 2. The outbox, so you never lose the event. The API has to update the database and emit an order-created event. Do those separately, and a crash in between leaves them inconsistent, exactly the dual write bug from a couple episodes back. So instead, both writes go in one transaction, the order row and the outbox row. Then, change data capture relays the event. The database is the source of truth, so the event exists if and only if the order was actually saved. No phantom orders, no missing events. Part 3. Per order ordering. We send every event keyed by the order ID. That guarantees all events for a single order land in the same partition and get processed in sequence. So an order cancelled event can never overtake the order created event it refers to. Related events stay in order, while unrelated orders still process fully, in parallel, across partitions. Part 4. The saga, coordinating the multi-service workflow. Reserving stock, charging payment, and shipping span 3 services with no shared transaction. So we model it as a saga with compensations. Order created triggers inventory to reserve stock. Stock reserved triggers payment to charge. Payment charged triggers fulfillment to ship. And on the failure path, say payment is declined, a compensating action fires. Inventory releases the reserved stock, and the order is marked cancelled, and the customer notified. For a short flow like this, choreography, services reacting to events, is a clean fit. And there's one final step that must never run twice. The actual shipping call to an external provider. We protect it 2 ways. We pass an idempotency key on the shipping request, which many providers will dedupe on. And we use the inbox pattern, recording the processed event's ID in the same database transaction as the shipped status, so that a redelivery becomes a harmless no-op. Now, in a real interview, they'll ask about scale, so have the napkin math ready. Say 50,000 orders per second. At roughly 1 kilobyte each, that's 50 megabytes per second of ingest. With a replication factor of 3, that's about 150 megabytes per second of cluster writes. At around 10 megabytes per second per partition, you need roughly 24 partitions, which sits comfortably on a handful of brokers. And conveniently, 24 partitions also supports up to 24 executor instances working in parallel. And to close it out, what do you monitor? Consumer lag on the order events topic. Are orders piling up unprocessed? Dead letter queue depth. Any poison orders to investigate right now? Saga failure and compensation rate. Is something in the workflow or a downstream breaking? And end-to-end latency at the 99th percentile. Is this slow in a way customers can feel? There it is, a complete, correct order pipeline, built entirely from patterns you already know. Idempotency, outbox, ordering, saga, and inbox dedupe. Next episode, we build something with a much tighter clock. A real-time scoring system that has to make a decision in under 100 milliseconds. See you there!